If you mention Bigfoot, most people immediately picture campfire stories, blurry photographs, and deeply ingrained folklore. Because of that cultural baggage, the subject is almost never evaluated with the actual rigorous tools biologists use to study confirmed wildlife. Researchers are now treating these sightings as a collection of raw wildlife data to construct a theoretical biological profile. Their primary methodology is called ecological niche modeling, or ENM. It works by taking the exact geographic locations of reported sightings and correlating them with sets of environmental data layers, like forest cover and rainfall, to predict where a species could survive. By stripping away the campfire legends and running the numbers through an ENM, scientists can test if a large, undiscovered primate is physically and geographically feasible in North America. To build a habitat map, scientists take these ENM predictions and apply them to the vast, rugged landscape of the Pacific Northwest. This pie chart shows the specific weighting system used to predict habitat. The model scores 5 criteria: forests at 40%, population density at 30%, and highways, lakes, and rivers each at 10%. The two heaviest indicators are heavy forestation and human population density. But compiling this data quickly reveals an anomaly. Out of 370 reported sightings used in the analysis, 196 actually occurred in densely populated urban areas. Assuming these urban encounters are human misidentifications, researchers remove them from the dataset to better isolate the core wilderness habitat. This data scale shows how they enforce that filter using a raster calculator, which is a tool that applies math to geographic maps. They reclassify the map's outputs, explicitly excluding the lower scores of 1.5 through 4.9, while keeping only the highly viable scores of 5 through 9. This rigorous filtration of the geographic data strictly isolates the creature's viable footprint to deep, unpopulated wilderness. So the habitat modeling tells us where it should live. To figure out what it actually is, we have to shift to micro-level biomechanics, using the famous Patterson-Gimlin film as a source of raw physical data. Analysts can calculate the subject's walking speed by isolating a specific 46-frame sequence in the footage, spanning from frame 307 to frame 352. This chart compares the resulting speed calculations. In that 3-second interval, the subject covers 16.6 feet. That translates to a walking speed of 3.85 miles per hour, significantly faster than the human average of 3.1 miles per hour. Next, they analyze the subject's overall physical size. Based on site measurements, the figure stands at an estimated 94 inches, or nearly 8 feet tall. To see if an 8-foot human is plausible, anatomists use a skeletal ratio called heads tall to measure body proportions. Normal human adults are generally 7.5 to 8 heads tall. As these silhouettes show, the film subject possesses extreme, non-human proportions. Due to its massive width and bulk, it measures only 5.9 heads tall. The morphological data extracts a subject that is considerably faster, taller, and more robustly proportioned than standard human biology allows. Now we have to compare the two halves of this profile. Does the physical morphology we see on film actually make sense inside the theoretical habitat mapped by the computers? Could a creature of this immense size, moving at that speed, realistically remain undiscovered in the Pacific Northwest? The answer lies in the biology of survival. An 8-foot-tall organism moving at a brisk 3.85 miles per hour burns immense calories and requires extreme wilderness and dense temperate foliage to sustain itself while remaining hidden. Those massive physical proportions correlate directly with the high forest and low population requirements isolated by the raster calculator. The geographic ecological niche modeling and the anatomical breakdown of the film subject point independently to the exact same highly specialized ecological footprint. Filtering geographic and morphological data reveals a subject that is biologically consistent with its environment. The parameters of the legend align with a specific functional ecological niche.